Hello, everybody. I believe it's our 30th lecture, and we're getting started just a little bit late. The door was locked, so I'm sorry. We probably won't go the full 50 minutes today, so we'll come close. I want to start off by saying that you've turned in homework 4 and give a little bit of information in terms of what's going to happen for the remainder of the term. So, first thing is, we will have one more homework. So homework 5, I'll probably get it next week. Pretty soon, early next week. And then second, looks like test 2 will be on April 29th. I think that's a Wednesday. Let me check very quickly. Yes, it's a Wednesday. I'll give you a study guide for that next time on Monday. Thirdly, we still have a final exam. I've forgotten the date. It's on your syllabus, and I'll start announcing it as we get closer to it. That's the 3 things that are left. So the final exam is worth 200 points. Test 2 is worth 100 points, and this will be worth in the 20s or 20 points, something like that. So we still have 320 points left. So that's a lot of points still left. So if your grade isn't what you'd hope for it to be, there's still plenty of room to improve it. If your grade, if you're happy with it, there's still plenty of room to even improve it from there. So that's what I wanted to tell you in terms of what's left. Last class, we proved several algebraic combinations, facts, involving limits of functions. That is, if you had the limit of f and the limit of g, then when you add f and g, that limit of that addition function exists, and it's equal to the limit of f plus the limit of g, and so forth. Same thing with subtraction, multiplication, and division, provided the bottom function is never 0 in the domain, or the limit of the bottom function isn't 0. So we had those combinations. I believe, just in case we haven't done it, as a fact, the limit as x goes to c of x, I'm sure we did this. What's the limit as x goes to c of x? I mean, we did this a long time ago, I think. When we first were introducing limits. Maybe we didn't do it. It's equal to c. If we did do it, we're going to do it again. Okay? And so how would we prove this? Well, we let epsilon be greater than 0 be given. We need a delta. Remember, we're talking about a limit greater than 0, such that for all x in a, here a is r, because the function f of x equal to x is defined over the whole real line, with 0 less than x minus c less than delta, then f of x, well in this case f of x is x, minus what it's equal to, what the limit we suspect is, which is c, will be less than epsilon. So we need this delta such that when x minus c inside absolute values is less than delta, that means that x minus c is going to be less than epsilon. Wait a minute. I get to control how close I want x to c. And however much I control it, I want it to be something such that it forces x minus c to be less than epsilon. What should delta be? It's right in front of us. What do you think, Chuck?
C?
No, not C.
No, because it goes 0 there.
So look, I get to pick this. I get to say, well, let x minus c be less than whatever I want. Whatever I let it be, x minus c be less than, I hope it implies that x minus c is less than epsilon. I want x minus, I get to say how close x is to c. I can say x minus c is going to be less than whatever I want. Whatever I say, I hope it implies that x minus c is less than epsilon. What should I let delta be? Epsilon. Right. So we just let delta equal to epsilon. That's the proof. I needed a delta, use the epsilon that was given to you. That's right. Okay. I know, as a fact, we did this before, the limit as x goes to c of a constant function is that constant. I know I did that. Okay. With those types of facts, the algebraic properties of function limits, the limit as x goes to c of x equaling c, and the limit of the constant equaling to the constant, then, as a fact, we'll get the following. If f of x is a polynomial function, so if f of x is a polynomial function, what's a polynomial function? Let me remind you what that means. That means that f of x has this type of thing. Is some number, that's a constant, times x raised to a natural number, plus some other number, times x raised to one less power, all the way down to a sub 1x plus a sub 0. And a's could be 0. Okay, the index could be 0. And so that's the form that it looks like. Then, the limit as x goes to c of f of x equals to f of c. Okay. And here's the way I'm going to argue through it. I'm not going to write anything down. It's just the way that I'm going to express why it's true. Look, if you want to take the limit of f of x, you take the limit of this expression. The limit of an addition is equal to the addition of the limits, provided each limit exists. Why does the limit of each term exist? Well, what's happening in each term? What's happening right here? What do you see going on? We adding things right here now. What are we doing between these guys? Multiplying. The limit of a multiplication is the multiplication of limits by the algebraic properties, provided each limit exists of the function. Well, the first thing involved in this multiplication is a constant. What's the limit of a constant? The constant. So this limit exists. What about x to the n? Well, x to the n means x times itself how many times? N times. So really, it's a limit of a multiplication, but through induction, we can say the limit of any type of multiplication, finite multiplication, is equal to the multiplication between the limits, and the multiplication, and the limit as x goes to c of x each time, we just said over here is x goes, is what meant? C. So every time you're going to get c here. And so it's going to be c to the n. So it's a sub n, c to the n when you take the limit of this part. Likewise, this is a sub n. You should say a sub n minus 1. I got excited. a sub n minus 1, c raised to the n minus 1. And that's what's going to continue on. Each one of the x's, you're just going to replace it with c. And so you get f of c. Is that okay? So example, if I say what's the limit as x goes to 3 of 2x squared minus 3x plus 5, the answer is, well, it's 9, it's 18, minus 9 plus 5, I think that ends up being 14. So that's the answer. You just stick in C. Is that okay for a polynomial? And that's what we have. As also a fact, if R of x is a rational function, what's a rational function? Anybody remember what a rational function is? I don't think I should remind us.
2 integers over.
That's what a rational number is. It's an integer over an integer. Similarly, we define a rational function to be a polynomial over a polynomial. Okay, so polynomial over polynomial. And g of c is different from 0, then the limit as x goes to c of r of x equals to rc. Here I'll just say g of x is different from 0. Let's just take the route. Never 0. And this again is the algebraic properties of the limits of functions in action, where the top's a polynomial, the bottom's a polynomial. And the limit of the top, the limit of a fraction is equal to the fraction of limits provided each exists, and the limit of the bottom is 0. It's not going to be here. That's nice. That's what these properties give us. They give us a whole class of functions I can evaluate their limits very quickly without having to use the definition. Let somebody force me to use the definition. Okay. Does anybody have any questions about that? You know, we had this other big theorem that we did in lecture 28, the day that I lectured without anybody being here. And that big theorem was the sequential criteria for function limits. And it related function limits to sequences of functions. And like sequence of functions of conversion, not sequence of functions, sequence of numbers, like sequences of real numbers, we're going to have some analogous facts for limits of functions. In particular, you might remember, if we had a convergent sequence, and each term of the sequence was between the numbers a and b, the limit of that sequence had to be between a and b. Well, we say the same thing here for a limit, essentially, through this fact. It says let A be a subset of R. Let F go from A to R, and let C be a cluster point. Of A. Okay? If A is less than or equal to alpha of x, which is less than or equal to b, and that's true for all x element of A, with x different from c, so we're going to not worry about x being equal to c. And if the limit as x goes to c of f of x exists, then that will tell me that the A will be less than or equal to the limit as x goes to C of f of x, which will be less than or equal to B. We're about to write that down. Okay, I said this was an analogous statement to what we have for sequences of real numbers. Very analogous. You know, if you have a sequence that converges, and each term of the sequence between A and B, what it converges to is between A and B. We're saying the same thing for limit of a function. If the function's values, output values between A and B, and the function has limit at C, then that limit is going to be between A and B. And the reason that's true is because of the sequential criteria for function limits, because those things are related. Does this fact kind of remind anybody where we're going? What we did with sequences? We had this fact for sequence, then we had another big fact for sequences. You think about that. I hope everybody understood what I was asking. You know, if I had sequence, if the sequence is between A and B converged, then the limit had to be between A and B. That's for sequences. And then afterwards we had another fact about sequences. Immediately afterwards. Mm-hmm. That's right. And now we're going to have a squeeze theorem for functions. Exactly. And it's going to be related to sequences through the sequential criterion for function limits. All right, well, let's prove this first. So we're going to let A be a subset of R. Let F go from A to R, and C be a cluster point. Okay. Okay. So we've got the most of the hypothesis. We also need to assume we're going to let A be less than or equal to f of x, less than or equal to b, and that's true for all x in the domain except if C happens to be in the domain. We want to show, oh no, there's another thing we've got to suppose. What else we've got to suppose? We have to suppose, we have to let, we're also assuming the limit as x goes to C of f of x exists. So let's call it L. Let's say it exists. Say this limit equals to L. Okay. Now, what we want to show is that the limit as x goes to C, well, I'm sorry, we want to show that A is less than or equal to L is less than or equal to C. Okay, how are we going to do this? Well, since the limit as x goes to C of f of x equals to L, then for any x sub n that's a subset of A, it's a sequence, such that with x sub n being different from C for all n element natural numbers, and the limit as n goes to infinity of x sub n equals to C, we have, what do we have? What are we going to write? What am I using here? I'm relating limits of functions to sequences. What factor am I using? What's it called? Yeah, the sequential criteria for function limits. That's right. And what are we going to have here? It's going to say that the limit as n goes to infinity of f of x of n equals to L. That's what it's going to have. Okay. Is that okay with everybody? Now, f of x of n is a sequence of output values. F of x of n is a sequence of output values. So, for every n element of the natural numbers, we have a is less than or equal to f of x of n, which is less than or equal to b. Because we're assuming that the f of x are sandwiched in between a and b. Well, wait a minute. That's only true for all x's except for when x might be c. But our sequence x of n that we're using is one that's a subsequence or subset of a that converges to c, but it also has the criterion that none of its terms are c. And that's part of it. So this is true for all n element natural numbers. And so by a fact, previous fact about convergent sequences. That means whatever this guy converges to has to be between A and B. And that is what we wanted to show. And that ends that proof. Does anybody have any questions about that? Okay. Well, let's look at the next theorem we want to prove. And that is the squeeze theorem. It says something very similar to what we just had. So here's the squeeze theorem. For function limits. Here's what it says. It says let F, G, and H all go from A to R. Let C be a cluster point of A, and suppose that f of x is less than or equal to g of x is less than or equal to h of x for all x element of A with x being different than c. Got some more. If the limit as x goes to c of f of x equals to L, which also equals to the limit as x goes to c of h of x, then that forces the limit as x goes to c of g of x to be equal to L. That's the squeeze theorem for functions. Pictorially, it's beautiful. Let's say this is our C. And what we're looking at is a situation where we've got three functions. We've got a lower function, middle function, and a top function. And let's just say I have an open circle here, or closed, it doesn't matter. Let's say this is L. And here's my bottom function. That's the F. And here's my top function. That's something like this. That's my H. And here's G. G's in between. And you see G is squeezed down to that Y value of L. It's funneled by F and G to go towards L at C. Is that okay? That's what happens. So here's the proof. Well, we're going to assume the conditions. So we're going to say we're going to let A be a subset of R. I'm sorry. Yes. F, A, G, and H go from A to R. C be a cluster point of A. The limit as x goes to C of f of x equals to L, which also equals to the limit as x goes to C of h of x. We want to show the limit as x goes to C of g of x has to equal to L. I sure do. I sure do. I sure do. If I don't, I'm making a mistake. Thank you very much, Audra. Where f of x is less than or equal to g of x, which is less than or equal to h of x, and that's true for all x element of A, with x being different than c. Yes, I am. I sure do. Okay, so that's all the hypothesis and what we want to show. All right, how are we going to show it? How are we going to show L is the limit as x goes to c of g of x? Well, it's called the theorem we're trying to prove is the squeeze theorem for function limits. And we have an analogous statement. It's called the squeeze theorem for sequences. And we have a way to relate them. How do we relate them? Yeah, the sequential criteria for function limits. So that's what I'm going to use here. So here's what I'm going to say. Since I'm going to do it this way. I'm going to let x of n be a sequence in A with x of n being different than c, and that's true for all n element natural numbers, and the limit as n goes to infinity of x of n equals to c. Since the limit as x goes to c of f of x equals to L, what can you tell me about the limit as n goes to infinity of f of x of n? What's that equal to? So look, as x goes to c, f of x goes to L. We know that, we're assuming that. And what else? I have x of n's getting really close to c. So what does f of x of n's get close to? Say that again. Not L of c. L is a number, not a function. You know, what this says is, as long as the x values are really close to c, as long as the x values are really close to c, the output values are really close to L. Here, the input values, x of n, are really getting close to c. So what do their output values get really close to? No, not c. The output values for f of those. Say it again, Chuck.
L.
L. I know you guys wouldn't say that. You wanted to keep the L out of that. That was funny. By what theorem? I mean, what is this the conclusion of? What did I just use? What relates limits of functions to convergent sequences? By the what? Yeah, criterion for function limits. That's the reason. Similarly, not only can I say this about f of x of n's, but I could also say, similarly, since the limit as x goes to c of h of x, the bigger function, equals to L, then what can you tell me about the limit as n goes to infinity of h of x of n? What's that got equal to? L, that's right. Why? By the, yeah. Okay. So that's what we have. So we got these sequences. For any sequence we get that's in A, none of its terms are C, and the limit of the sequence is C. We have f of that sequence goes to L, and h of that sequence goes to L. Since x of n is always different than c, and f of x is less than or equal to g of x, which is less than or equal to h of x. Well, that's true for all x in A with x being different than c. Well, it just so happens all the x of n's are different than c. Then we have f of x of n is less than g of x of n, g of x of n, which is less than h of x of n. What's the limit of this? This is a sequence. Okay? What's the limit of this guy as n goes to infinity? L. What's the limit of this guy as n goes to infinity? We're talking about sequences now. So what's the limit of the middle sequence got to be? 1. That's correct. By what fact? So this equals to L, why? What are we using? What are we talking about over here? We're talking about sequences. We're talking about some fact related to sequences. What fact are we using? It's a sequence fact. It's the squeeze theorem for sequences. Right. So I got the limit as n goes to infinity of g of x of n equals to L. Great. What was I trying to show? I was trying to show the limit as x goes to c of g of x equals to L. And that's what I'm trying to show. But wait a minute, what did I just show? I showed that if you give me any sequence in A, whose none of its terms are C, and yet the sequence converges to C, that forces g of that sequence to go to L. That's going to imply that the limit as x goes to c of g of x equals to L. Why? What fact is it out there, Chuck, that if every sequence that you look at where none of its terms are c, but it converges to c and it's in the domain of the function, if f or the function g evaluated that sequence goes to L, implies that the limit as x goes to c has to be equal to L. What fact are we using? What am I relating? I'm relating a sequence to a limit of a sequence to a limit of a function. What relates that? What fact?
Criterion.
By the
Sequential criterion.
for function limits. And that's, I got what I want. Limit as x goes to c of g of x equals to L. That's it. That's what we're trying to show. Put the box. That's it. So you see that we're relating limits of functions to sequences, limits of sequences. And we're doing that through the sequential criterion for function limits. Is that okay with everybody? Okay. Well, good. Does anybody have a question? Give me stuff to say. Yeah, Chuck.
I got a question. This feels silly, but how do you know that f of x of n, g of x of n is between h and f of x of n?
Because in the assumption, you might remember, that's a good question. In the assumption, we were assuming that f of x is less than g of x is less than h of x. I didn't write it down to start off with. Audra reminded me, hey, that's part of the problem, isn't it? And that's the reason. So it says, no matter what input value you put here, f of it is going to be less than g of it, which is less than h of it. That's what we're assuming. Except for one possible input value, which was c. And so that's why it's important that we know that the x of n's are never c.
Okay.
That's all right?
Yep.
It's a good question to ask about. Anybody else?
We did it through relating limits of functions to limits of sequences, but is there a way that you don't have to involve sequences at all?
I think you can with epsilons and deltas. I think they can be.
Okay.
We didn't do that partly because we want to show why it's nice to work with the sequential criteria for functional limits. Why do we have that theory? It's because it can help us get other things. So this is some of the things it can help us get. But it may not be the only way to get these other facts. Yes, Audra, I'm pretty confident you can provide a different proof. A different proof can be provided with just epsilon and deltas. Okay, I'd like to next look at example. So we got this squeeze theorem. See if we can use it. show, so here's an example. The limit as x goes to 0 of x times sine of 1 over x equals 0. That's what I want. Ladies and gentlemen, I want to tell you that this function right here is what we're taking the limit of. X times sine of 1 over x. It is not defined for x equals 0. It's not defined because I can't divide by 0. Okay? When you're taking a limit, remember we're talking about all x is close to c, but not equal to c. And the way that the not equal to there in the definition is 0 is less than the absolute value of x minus c is less than delta. Is that 0 less than the absolute value point? It says x in c. We don't care about what happens in c. So c is a cluster point for the domain of this function. The domain of this function is all real numbers except c, except 0. And c is a cluster point for that domain. So I could take this limit. I don't know whether it exists or not. The sine of 1 over x, as x values get really close to 0, it's going to force sine of 1 over x to oscillate between minus 1 and 1 very rapidly. So it's bouncing up and down a lot. Is that okay with everybody? But it's bouncing up and down between what numbers? Not 0 and 1, but I'm just talking about sine of 1 over x. What does sine bounce from? Graph of sine. What's the smallest thing sine can be? Negative 1. What's the biggest thing? 1. So I want to show that this is equal to 0. Now I'm thinking that this is an example of the squeeze theorem. So I'd like to have this be my g of x. I'd like to have something smaller, a function smaller, that I know goes to something, and some function that's always bigger, except maybe x, that goes to the same something. And that will force the middle, x times sine of 1 over x, to go to the same something. Okay? So I got to relate this to something I know. But listen, you guys just said that sine of 1 over x, that's going to be sandwiched between which numbers? Negative 1 and 1. Okay. And here's what I want to say. That's true. Okay? No doubt about it. And this is true for all x element of R with x different from 0. Because we can't have x be equal. It fits just perfectly. So if the limit of this guy exists, it's somewhere between minus 1 and 1. The limit of this guy doesn't exist. Okay, it bounces too wildly. It doesn't exist. But it's some part of the problem that I haven't gotten involved yet. And that's the multiplication of x. So somebody can think, well, let's just multiply everything by x. Then we'll get exactly what we want. Minus x less than or equal to x sine 1 over x, which is less than x. But the problem is when you multiply by x, you don't know whether x is a positive or negative number, especially if we're going towards 0. Parts of it is positive, parts of it is negative. And why is that important? Is that we're multiplying an inequality by some symbol. And when you multiply an inequality by some symbol, you might have to change the inequality if you're multiplying by a negative. Is that okay? So here's what we'll say. So let's consider some cases. Consider, here's case 1. If x is, let's say less than 0, then we have minus x is greater than or equal to sine, will be x times sine of 1 over x, which will be greater than or equal to x. So I multiplied everything by x. I flipped the inequality because I multiplied by a negative number.
Why doesn't x
Well, x is negative.
okay.
So here, I'm just multiplying everything by x. Minus 1 times x is
Okay.
minus x. But I got to switch the sign of the inequality. I don't like the way I wrote it. It's okay, I didn't write anything wrong. So, if x is less than 0, we have, I'm just going to write it down kind of in a more usual format for me. X is less than or equal to x sine of 1 over x, which is less than or equal to minus x. I just switched, everything. It's still the same statement. I just put the smallest guy to the left. Now here's what I want you to notice. Chuck, think about the situation that x is less than 0. Okay, x is a negative number. What if I were to ask, what's the absolute value of x, Chuck? X is negative. What's the absolute value of x? Well, it would be.
Oh, that'd be minus x.
Okay, so this right here is the absolute value of x. Is that okay with you? And this right here would be minus the absolute value of x. So this is a true fact. Okay? And it's true when x is less than 0. Well, what about the case where x is bigger than 0? We'll get out in a second. Suppose, for case 2, x is greater than 0. Then, since minus 1 is less than or equal to sine 1 over x, which is less than or equal to 1, we have, this is true for x being different than 0, we have minus x is less than or equal to sine x, or sine 1 over x, which is less than or equal to x. In terms of absolute value in this case, x is positive. So the absolute value of x is, yes, positive. But what is it? What's the absolute value of x if x was a positive number? X. So this is the absolute value of x. So we have minus absolute value of x is less than or equal to sine 1 over x, which is less than or equal to the absolute value of x. So in all possible cases, we're almost done. We have.
I have a question.
I'm ready.
Is there a reason you didn't multiply sine of 1 over x?
Oh, no, I made a mistake. Right here, there should be an, yeah, there's the reason is I made a mistake. Thank you very much, Chuck. Chuck, I'm going to give you $1.
Okay.
Boy, he didn't pass it up. I tell you, I said, Chuck, I'm going to give you $1. No, I can't take that, Professor Wood. He said, no, I'll take it. I want it. No, I'm not passing that by. So in all possible cases, we have minus absolute value of x is less than or equal to x, sine of 1 over x, which is less than or equal to x, when for x being different than 0. Okay? And that's what we're talking about. So here's what I'm thinking is my f is minus absolute value of x. Here's what I'm thinking is my h is the absolute value of x. Let me finish it up. One more minute, I'll be done. I'm not going to go into the details here. I'm just going to say this. Note, the limit as x goes to 0 of minus the absolute value of x, it equals to 0. And the limit as x goes to 0 of the absolute value of x, it is also 0. I'll prove that next time. So by the squeeze theorem, what's going to be the limit as x goes to 0 of x times sine of 1 over x? Remember, it's in between these two guys. So it's got to be equal to 0. That's it. let you have a chance to write that down. I thank you very much. That will conclude this lecture. Told you we wouldn't go full 50 minutes.